Gases differ from liquids and solids, and one of the biggest things that we see is that gases are compressible, meaning you can decrease their volume and you'd still see the same amount of gas molecules moving around. Now, we're also going to learn in this chapter how pressure, temperature, and the amount of gas molecules have an effect on the volume of them. Now, there's many different units of pressure. Some units of pressure that we're going to use very often are atmosphere, and this mmHg is millimeters of mercury. We're going to be using torr often. We don't oftentimes use bar, but you may see that in a problem. And then P, capital P, little a is Pascal. Now, there are some conversion factors that you're going to need to utilize depending on what equation you're using. So again, a couple popular ones is 760 millimeters of mercury is equal to 1 atm. We're going to use that. And 1 atm is equal to 101,325 pascals. So those are two common ones. Of course, there are multiple other ones that we're going to utilize. Now, in olden days, they were calculating pressure using this barometer. So how this worked is what this was filled with was actually mercury. So Hg is the symbol for mercury. And what happened here is this was an open container of mercury, and this was a closed tube. And so when the pressure of, the atmosphere was heavier, it would push down more on this mercury liquid inside the open container, and therefore the pressure would increase inside the tube. And so this didn't have any air in it, which did not affect, therefore didn't push down at all. So all we looked at was the height in this tube, which is where that millimeters of mercury pressure unit comes from, is literally how many millimeters of mercury this tube was exhibiting, depending on the different weather. So there are a couple gas laws we're going to be utilizing. We're going to look at Boyle's, Charles, Gay-Lussac's, and Avogadro's. And a couple terms we're going to be using is inversely proportional and directly proportional. And we'll discuss what they mean in terms of different variables. Now, another equation that we're going to utilize for most of the problems here is Kelvin equals degrees Celsius plus 273. Sometimes you'll see 273.15. You can use either one. And this is because Kelvin is the unit that we need to use for every single gas law problem. So the first one is Boyle's law. And so what Robert Boyle discussed was the volume of a sample of gas at constant temperature, meaning the temperature is not changing, is inversely proportional with applied pressure. So what does this even mean? This means for gases only, when you increase the volume, that means the pressure is decreased. So inversely proportional means as one variable increases, the other decreases. And that can obviously go the other way. As one decreases, the other increases. So volume and pressure in terms of gases have this inverse relationship. Now, to write an inverse relationship, you can go ahead and write the first variable. It doesn't matter which one you choose in this case. And then you go ahead and put this proportional sign. And then we put a 1 over because, again, as one increases, the other is decreasing. Okay? Now, you are not really going to utilize this equation. This is just explaining what inverse means. The equation that you will be utilizing is this PI VI, and these are multiplied together, equals PF VF. Now, I have always used P1 times V1 equals P2 times V2. The I's in this case mean initial and the F's mean final. It doesn't matter which one you use as long as you understand it is the initial pressure and the initial volume then equals another set of circumstances, pressure and volume. Then we're going to go ahead and demonstrate this equation with this problem here. So we have a volume of oxygen gas, and it occupies 38.7 milliliters. So immediately when I'm working with these problems, I like to kind of underline or highlight the relevant information as I go through the problem. And I also like to indicate what variable it is because you're going to have to figure out what equation to use depending on the variables provided. So if I see 38.7 milliliters, I'm going to go ahead and immediately put a V for volume because liters is volume. And at 751 millimeters of mercury, and that is a pressure at 21 degrees Celsius. So I'm going to go ahead, and that is a temperature, obviously. And remember, we're going to have to change this to Kelvin. We can never, ever, ever use Celsius in this entire chapter. Now, what is the volume? So this is what we are looking for. We are looking for volume. If the pressure changes to this amount, I'm actually going to go ahead and change my highlighting color here. 359 millimeters of mercury, and that is a pressure, while the temperature remains constant. Now, that does mean that this temperature is not changing. When the temperature is not changing, you don't have to take it into account because you'd be multiplying and dividing by the same number. And I'll show you that here in a moment. So what we're really working with is a volume and a pressure, and we're trying to calculate a new volume with a new pressure. So this is going to be an example of Boyle's law. Now also, when in doubt, go ahead and make yourself a chart of the variables. I'm going to go ahead and fill in this chart. So I have 38.7 milliliters. And units for volume don't matter in this as long as the units on the initial and the final are the same. So this is milliliters. This means this will end in milliliters when we solve for this. The pressure is 751 millimeters of mercury, and my new pressure is 359. Again, this unit doesn't matter for pressure or volume as long as they are the same. If one was ATM and the other was millimeters of mercury, you'd have to convert. It wouldn't matter what you converted to as long as they were both the same, because they'll cancel each other out. And then we know the temperature changes. Remember, I'm not going to write 21 here, but I'm actually just going to quickly add, remember my equation is Kelvin equals degrees Celsius plus 273. Now, I did tell you you don't need to take that into account because it is the same, but I'm just demonstrating to you how you would know that. Because it is 294 Kelvin on both of these, you can actually just not account for it in your math, okay? Because it doesn't change. When something remains constant, it's nothing we need to calculate. Now, let's go ahead and put it into our equation here. So we have P1, V1. Again, if you want to do PI for initial, that's fine. I've just done this since high school, so it's just been stuck with me. V2. And so 1 just means the initial or a set of circumstances, and the 2 means the other set of circumstances. So let's go ahead and set this up. 38.7 milliliters. I like to keep the units in here because it just confirms that they are the same. Not necessary, as long as you've kind of checked it prior. 159. Running out of room, so I'm going to write that down here. And then we're looking for V2 or V final. So I'm going to go ahead, and how I'd solve for this is I would multiply this left side, okay, get an answer, and then I would divide that by 359 to get rid of it, the variable next to the V2. And I went ahead and solved that for us ahead of time, and my answer ends up being 81 milliliters. Now let's just do a quick check knowing our relationship. So I had an initial volume and an initial pressure, and what happened to my pressure is I decreased it. If I'm decreasing my pressure, Boyle's law is inversely proportional. So if I decrease my pressure, my volume's going to increase. So did my volume increase? Yes. From the initial 38.7, it's now 81. So that's just a nice check to make sure you know the relationships and that your answer seems reasonable. Another law we're going to look at here is Charles' law. Charles's law is, I believe there actually should be no S here. This is why I don't teach English. Okay. Charles's law is directly proportional, okay? And directly proportional means as one increases, the other increases. So this is a nice standard relationship between volume, okay, and temperature. And when it says at a constant pressure, that just means we are not affecting pressure, no change in pressure in these circumstances. So again, this is the relationship between volume and temperature. Remember, temperature has to be in Kelvin. I'm going to say that a million times, but this entire chapter immediately just convert to Kelvin. Okay, don't put any thought into it, just convert to Kelvin so you don't forget. Now, the way we demonstrate a direct relationship here is the proportional sign next to the V and the T, and they are directly V. As you increase V, you increase T, or if you decrease the other. Now, the equation here is VI over TI equals VF over TF, or V1 divided by T1 equals V2 divided by T2. And again, the only thing that you have to care about a unit for is the temperatures. They have to be in Kelvin. It does not matter what the volume units are as long as they are the same, okay? So if one was torr, the other one has to be torr. You can convert. It doesn't matter which one you convert unless the problem asks you to convert into something. Now, I like this demonstration of the relationship between volume and temperature. So if we had, you can actually do this here. If you blow up a balloon and you stick the balloon in liquid nitrogen, just the fumes of liquid nitrogen, which is very, 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 very cold, the low temperature is actually going to decrease the volume of the molecules because they are not going to move as quickly. So since they're moving less quickly, they're kind of sluggish. They don't take up as much room. So the balloon would deflate a little bit. If you go ahead and keep it out of this liquid nitrogen in room temperature, it actually would reinflate to what it originally was. So you're not causing any harm to the balloon, but that difference in temperature has a direct relationship to the volume. Let's go ahead and practice a problem here. So you prepare carbon dioxide by adding HCl to marble chips. According to your calculations, you should obtain 79.4 mils at 0 degrees Celsius. So I see a volume and I see a temperature. Now immediately I'm going to say, hey, I need to convert this. This is 273 Kelvin. I like to do that right away. How many milliliters, so I'm looking for a volume 2 or a volume final, of gas would you obtain at 27? So I'm going to go ahead and convert my 27 to Kelvin. So it's 300 Kelvin. All right, I'm going to go ahead and set myself up a chart. So 79.4 milliliters and 273 Kelvin. I'm trying to look for my VF or my V2, and my temperature final is 300 Kelvin. Now, I know this is a small little tidbit, but Kelvin doesn't have a degree symbol. It's an absolute value, so if you try not to put it, if we're learning this correctly, if you do, of course, no big issue, but just so that you learn it correctly. Again, a reminder, it has to be in Kelvin, where the other units do not have to be anything specific except the same. So I'm going to go ahead and set this up to be 79.4 milliliters over 273 and 300 K on the bottom and a V2. All right, just a reminder how to solve this. I would go ahead and just make a division sign on my calculator and divide 79.4 divided by 273. I get an answer. And then to get this 300 out of the bottom, I'd multiply both sides by 300 and I'd be left with V2. So go ahead and make sure you try that on your calculator to make sure you're getting the same answer as me. And I got 87.3 milliliters. All right, and then we're going to look at Gay-Lussac's law, and this is another direct relationship here, and it is a direct relationship between pressure and temperature, again in Kelvin, and we see that relationship expressed here. Our equation here is Pi divided by Ti, Pf divided by Tf, or P1 T1 divided by P2 T2, okay? Or equal to P2 divided by T2. Now, we're also going to put all three of these variables in. We call this the combined gas law, and this doesn't change any of the relationships. We still know that the only inverse relationship we have is volume and pressure, which is Boyle's law, and the other ones are direct, which is a nice memory trick here. But our equation we can utilize when we have more variables in an equation is the combined gas law. P1 V1 over T1, PF VF over TF. Now, what units can we have? Well, it doesn't really matter, except these P's have to be the same unit, these V's have to be the same unit, and the T does matter. We are well aware that these have to be in Kelvin. Okay, so good check. Make sure you do any converting before you plug it in, just to make it easier on yourself. Let's go ahead and try a problem. So we have divers working from a North Sea drilling platform at 50 ATM. So I like to always kind of work through what variables I have here, and this is a unit of pressure at a depth of 500 meters. So we'll see if we need that. Usually distance isn't something we talk about too much in gases. There's usually extraneous information, so you have to kind of weed through what you need. If a balloon is inflated to a volume of 5 liters, so that is a volume, obviously, at the depth at a water temperature of 4 degrees Celsius, that is a temperature which I will convert, what would the volume be, this is what I'm looking for, of the balloon be on the surface, which they tell you what that is in millimeters of mercury, and then they tell you a temperature. So let's go ahead and kind of categorize our information here. So we have 50 ATM, and I have 5 liters, and I have 4 degrees Celsius, so that is 277 Kelvin. I just added 273 to that. And then my new volume is what I'm looking for, and my pressure is 755 millimeters of mercury, okay? And the reason why I like to do this, check this, is look, ATM, millimeters of mercury. They can't be different. They have to be the same, so they cancel out. So what I'm going to do, it doesn't matter which one you convert. I'm just going to quickly do a little conversion right here. Millimeters of mercury to ATM. You can write these, you can utilize these whenever you need them. So 1 ATM is 760 millimeters of mercury, so I go ahead and divide that. And when I divide that, go ahead and do that, I get 0.993. I'm going to go ahead and keep 3 sig figs, and that's ATM. And then my temperature final is my 273 plus 11, which ends up being 284. So let's go ahead and set up our problem here. I wrote the combined gas law up above, and I know I'm using the combined gas law because I have 3 variables in both situations. So my initial pressure is 50, and my volume is 5 liters, and my temperature is 277. I wrote this a little large. I'm going to move it over. And then I'm going to have to cram this in, but my pressure is 755. Oops, nope. Remember, we converted that to 0.993. And I'm looking for V2. And my new temperature is 284. Okay, so how I would solve this is I would actually go ahead and solve the left side. So I'd take 50, multiply by 5, and then get an answer and divide by 277. I then would multiply the number by 284 to get it out of the bottom. Okay, and then I can go ahead and solve for that variable, and I have that demonstrated right here. So I went ahead and multiplied and divided here, got this answer, and then I went ahead and multiplied actually by that 284, and this is the answer for multiplying by the 284, and then I went ahead and divided both sides by 0.993 and ended up with 258 liters. Now, how do I know the unit? That's a common question. Well, you have to go back. If my initial volume was in liters, that would make my... Another gas law we're going to look at is Avogadro's law. And Avogadro's law looks at 2 variables, V for volume, and a new one for us, N, which stands for moles of gas. And we're going to see that N in another common equation coming up soon. But what this relationship is direct, meaning as we increase the volume, we will also need an increase of moles to therefore maintain that same temperature and pressure conditions. And you can see here the equation of V1 over N1 equals V2 over N2. And we will see this relationship in an upcoming situation. Now, another sort of situational condition you may see is called STP, which stands for standard temperature and pressure. And when you see STP written in a problem, you have to understand that it means 0 degrees Celsius and 1 ATM. And so 0 degrees Celsius we know as 273 Kelvin, and 1 ATM pressure is actually what we exist at. So another situation you have to understand is STP can be used as a conversion whenever we are talking about a certain gas. So at STP, at standard temperature and pressure, we can utilize the relationship of 22.4 liters per mole. Now, what is nice about this is actually a conversion factor. So this means at STP, at 1 ATM of pressure and 273 Kelvin, there are 22.4 liters of gas in 1 mole. Okay, so we can see that and utilize that in a fraction situation. I'm going to go ahead and show you that here on the next slide. So find the volume of 15 grams of CO2 at STP. So here you go. It says STP. You have to understand that means 1 ATM and 273 Kelvin. Now, this is a pretty easy problem. The only thing you have to go ahead and utilize is changing your grams to moles because we know this relationship to be 22.4 liters per mole, which is the same as saying 22.4 liters per 1 mole. So I can't go ahead and convert grams directly into liters, but I can go ahead and do a quick conversion from grams of CO2 using molar mass, and I end up with 0.341 moles of CO2. And then I can go ahead and utilize my moles and use this conversion factor here. So I'm ending up just multiplying by 22.4, and my answer ends up being 7.64 liters. And let's be a little bit more exact with that and indicate the identity, which is CO2. Now, this is what I would say is the most important gas law of them all. It is called the ideal gas law, and the equation is PV equals nRT. All of these variables are multiplied by each other. Now, this is the only equation out of all the ones we've learned thus far that requires certain units for the variables. So let's go ahead and kind of go through those. So pressure, P is obviously pressure, and pressure is 2 unit options. It can either be ATM or it can be millimeters of mercury. Okay, or it actually could be torr, because torr and millimeters of mercury is a 1-to-1 relationship. Now, I'll tell you when you can use either one of these, but keep those in mind. So if you're in pascals or you're in bar, you have to go ahead and convert to either ATM or millimeters of mercury. Now, volume is very specific. It has to be in liters, not milliliters. It has to be in liters. Moles, of course, we know has to be in the unit of moles. So there is that N, again, that we saw previously in Avogadro's law. R is our gas constant. And so we have 2 gas constant options. I will put these on an equation page for you, so you do not need to memorize these. Now, their 2 options are 0.08, 206, and our units here are, and I have them written over on the left side here, it is liters times ATM divided by moles Kelvin. And then we have another one, which I'm going to go ahead and put the units down here, is liters torr moles Kelvin. Okay, so the only thing that is differing between these R values is the unit of pressure. Okay, right? Torr or liters is the same, moles are the same, Kelvin is the same, which we know we can't do anything about that one. So this 0.08206 is if your pressure is in ATM in the problem, or you convert it to ATM, or we have this second R value if your pressure is in torr. Now, just a quick note, and you can go back and confirm this, but 1 millimeter of mercury is equal to 1 torr, so that is why this 62.36 R constant can also be used with millimeters of mercury. Okay, so 2 of them, you have to decide which one you're going to utilize depending on your pressure unit. And then T, we are fully aware, has to always be in Kelvin. Okay? Let's go ahead and practice a problem here. So we have a 500 milliliter, which immediately is a volume cylinder of nitrogen, and it has a pressure of 1350 millimeters of mercury at 23 degrees Celsius. We know we need to be putting that in Kelvin. How many moles of nitrogen are in the cylinder? So I have a volume, I have a pressure, I have a temperature, and I need to solve for moles. This is a case for PV equals nRT. You may hear this called PivNert. I promise I didn't make that up. That is a very common way of saying it. So if you watched another video and see that, just a heads up. So let's go ahead and get our variables correctly labeled and put into the correct unit. So 5,000 milliliters needs to be put into liters. So that is 5 liters, 5.000 liters. There's 1,000 milliliters in a liter. Make sure you know that. And my volume, I'm actually going to leave in millimeters of mercury because I can use this second R constant because we know torr and millimeters of mercury are equal to each other. So I'm going to go ahead and write that. Now, you don't have to set up this little chart, but if you ever have trouble with these types of problems because they get a little bit overwhelming, I highly suggest a chart to just help you realize what equation you have, check all your units and all that. So I'm going to go ahead and add 273 to 23 degrees Celsius and immediately get 296 Kelvin. Now I'm going to go ahead and plug all these in. So my P is 5 liters. My V is 1350. I'm going to write it down below because I'm running out of room here. And my I'm actually going to move this whole thing over. Okay, and my N is what I'm trying to solve for, so I like to just leave it as N. My R constant, I'm going to go ahead and use the 62.36, and that is liters torr, or you could change that to millimeters of mercury. That's perfectly fine because we know they are 1-to-1, and moles Kelvin, and my temperature was 296. Okay. So how would I solve this? I'd first multiply the left side, so 5 times 1350. And then I'm going to go ahead and divide by whatever the product of the 62.36 times 296 is. And please be trying these on your own just to confirm you are doing the order of operations correctly. Now my moles, remember moles is a really small answer typically, and I'm going to go ahead and keep... I'll just keep 3 sig figs here. I'll try to be kind of specific with that. But again, that's just such a small thing. Typically we do 2, but that seems like I'm cutting it a little too much here. So I'm going to do 0.366, and don't forget my unit is moles. And let's just be a little more specific here with N2. All right, now, how many grams of diatomic nitrogen are in the cylinder? So just to remind you, diatomic nitrogen is just reminding you that it is in a form of 2 because it is more stable in that form. And they do tell you that here it is N2, so you can always go back and look. So let's go ahead and do one last conversion here from moles to grams. Okay, and so we have 28.02. That is 2 nitrogens added together. And we're going to go ahead and multiply that. Keep it 3 sig figs, 10.3 grams of N2 in the cylinder. Okay. You'll be using PV equals nRT a lot. It's a very common gas law problem. So just make sure you understand what R value to use and checking all your units, because other gas laws don't matter as much about the units as long as they're the same, but PV equals nRT does. Let's go ahead and look at one more problem here. If I have a tank with 0.875 moles of gas at a pressure of 1.2 atm and a temperature of 87, what is the volume? I went ahead and solved that down below if you want to go ahead and try yourself. But I have my pressure, which is an atm. I have my volume, which is what I'm trying to find. And I have my moles. Now I used the R constant that contains the atm pressure unit, 0.08206, and I went ahead and converted this to Kelvin. I end up with 21.5 liters. Again, please make sure you check your math. All right, now there are some manipulations of this PV equals nRT equation that we can go ahead and do, and I'm going to go ahead and demonstrate that to you. So some things you do need to remember and you will need to utilize, I will give these to you, is density is mass over volume. So little m here does not mean moles, it means mass. In the gas laws, we use N for moles, and I know that's confusing, but that's just consistently what it is. So density is mass over volume, and then big M is molar mass. And just to remind you, molar mass is in the unit of grams per mole, grams per 1 mole. And that is equal to mass divided by moles. So we're going to go ahead and manipulate this equation. I'm going to go ahead and show you how to derive this. So I'm going to go ahead and replace my N with this. I'm going to go ahead and write this actually a little bit better. Molar mass is mass over moles. Okay, and so if I rearranged this equation, I could rearrange this equation by multiplying both sides by N and then dividing by molar mass, and that would give me N equals mass, which is in grams over molar mass. So all I did was rearrange that equation. So I can go ahead and utilize that by putting that in this spot because N can be replaced. So let's go ahead and do that. So PV equals mass. You can put little m. I just put mass because there's so many N's and M's and all that in this that I like to just write the whole word for that one. So mass times R times T divided by molar mass. Now you may need to utilize this equation. So this is one, what we call rearrangement of PV equals nRT if you have to solve for molar mass or you are provided with moles. So that is a good way that you can utilize it. Now another way you can utilize it is to just go a couple more steps and include density in this equation. So to do that, I need to be able to replace a mass divided by a volume with D for density. So to do that, I'm going to actually continue on here utilizing this equation. So this is one of them, but I'm going to keep going. I'm going to go ahead and get this V. I'm going to divide both sides by V, so that equals P equals mass times R times T divided by V times molar mass. So all I did was move this V down at the bottom by dividing both sides by it. And then I can replace this whole bit with the D. So that equals pressure equals density times RT over molar mass. And so this is another derivation of PV equals nRT that we can utilize to solve for gas law problems that want us to solve for density or molar mass or has one of those. Okay, so we're going to go ahead and utilize those in some problems that we continue on in this PowerPoint. What is the density of methane gas? Methane gas is just natural gas. That's what shale drilling is. Methane has a formula of CH4, and we are given a temperature and a pressure. So what I'm going to go ahead and do is use my equation that I've solved for. I will not provide you with these equations, so you will have to know how to solve for them or have them provided to you in some method, depending on what course you're in. So we can go ahead and look at... I'm going to utilize the equation because I'm trying to find density, so I'm going to go ahead and use the second equation. So P equals density times R times T over molar mass. And so I'm solving for D, so my pressure is 1.25 atm. And looking for D, and I'm going to go ahead and use 0.08206 here because that is liters atm mole Kelvin. And then my temperature is 125 plus 273, of course. And that gets me 398. Okay, Kelvin. So I can then divide by my molar mass. And I know I made those units pretty large, but that's okay. Now, to get my molar mass, I can just add up 1 C and 4 H's. And so that is 12.01 times 4 plus 4.04. And that gets me 16.05 grams per mole. All right, now I'm going to go ahead and solve this. So I am going to get that 16.05 out of the bottom. So multiply 1.25 times 16.05 and up with 20.063 equals density times 0.08206. Now, sometimes I will tell you that sometimes you put the units in and it kind of hinders the math. It may be confusing. So if you don't want to put the units in, just as long as you're checking them before you're putting them in, that's okay. I like to do that just to be accountable, but you do what works best for you. So 20.063 divided by the product of 0.08206 times 398. And my density ends up being 0.614. Now, this is a little bit different. Density for gases, if you worked through all the problems, we don't have milliliters here. Density is typically for liquids grams per milliliter, but this is actually not. This is actually going to be grams per liter, and that is because we have no, we don't have any... I'm losing track of my thinking. No milliliters in this problem. We have liters present in our gas law constant, and then we have grams here. And you're always welcome to work through the units. If you'd like to see that at some point, please catch me and we can work through those units together. So my density, 0.614 grams per liter for methane gas. All right, let's go ahead and do one more problem here to continue on and throw together some empirical and molecular formulas with gases. And so we have a 500 milliliter flask, and I'd like to go ahead and write my variables. So that is going to be a volume containing a sample of octane, and we are placing it in boiling water bath in Denver, which has a much lower pressure, so this is a pressure value, and the water boils at 95 degrees Celsius. This is a temperature. The mass of the vapor is 1.57 grams. Okay, so they are giving me a mass, so that is 1.57 in grams. What is the molar mass? Okay, so we're looking for molar mass, and we're given mass, we're given temperature, we're given volume. So I'm going to go ahead and utilize my equation PV equals nRT, but I'm going to replace the N, just like we did a previous couple slides ago with mass divided by molar mass. And remember, that is a derivation of the equation N equals mass over molar mass. Okay, so we rearrange that. You can go ahead and look above if you need to remind yourself of that. So I went ahead and replaced it, and you can see that I plugged my variables in here. I kept millimeters of mercury because that is the same as torr, so I can use that 62.36 R value. And then I changed my milliliters to liters, of course, and I kept my 1.57 grams and converted my temperature into 368. Now I went ahead and solved for my molar mass. I got 114. Remember, molar mass units are grams per mole. So I answered the first question, what is the molar mass of octane? 114 grams per mole. Now, this is the molar mass of the molecular. Let me remind you the difference. Remember, empirical, which it's telling you here, is C4H9. This is the simplest form, okay? The lowest ratio of values is the empirical. It's not the true. It could be, but it's usually not. We are trying to then find the molecular formula, okay? So we're going to go ahead, and I actually have the work on the next slide here. So if we have our empirical formula, let me remind you of the equation here to go from molecular or empirical to molecular. So our equation is molecular formula, molar mass, divided by my empirical formula, molar mass. And this gets me a multiplier. Remember, a multiplier is then multiplied with the empirical formula subscripts, and we go ahead and get our molecular. So our molecular formula molar mass is what I just solved for in my previous equation, which is 114. You can see that here. And then I went ahead and added 4 carbons and 9 hydrogens up and got 57.13. That goes on the bottom. And my multiplier is 2. That is not my final answer. I'm going to go ahead and multiply that 2 by both of these subscripts to get C8H18. Okay, and this is called octane, oct meaning 8, so it makes sense that there's 8 carbons here. Just a nice little check. Thanks for listening.